Introduction to MAP. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving into the MAP family of IPv6 transition technologies, specifically MAP-E and MAP-T. MAP stands for Mapping of Address and Port, and these technologies represent a sophisticated evolution of the LW406 architecture we've discussed previously. MAP was developed by the IETF to provide a standardized, algorithmic approach to IPv4 address sharing that enables deterministic, stateless operation at carrier scale. The beauty of MAP lies in its mathematical elegance. It uses carefully designed algorithms to create reversible mappings between IPv6 addresses and IPv4 address plus port combinations, allowing ISPs to operate IPv6-only networks while providing seamless IPv4 connectivity to customers. The MAP family consists of two main variants: MAP-E, which stands for MAP Encapsulation, and MAP-T, which stands for MAP Translation. Both variants share the same core addressing algorithm and port set calculation methodology, but they differ fundamentally in how they transport IPv4 packets across the IPv6 network. MAP-E uses encapsulation, wrapping IPv4 packets inside IPv6 packets similar to what we saw with DS Lite and LW406. MAP-T, on the other hand, performs stateless protocol translation between IPv4 and IPv6, converting packet headers rather than encapsulating them. This distinction has important implications for deployment scenarios, operational characteristics, and compatibility with various network architectures. What makes MAP particularly powerful is its algorithmic approach to address and port assignment. Rather than requiring a provisioning system to assign each customer a specific port range and then maintain a central database of these assignments, MAP uses mathematical formulas that allow both the customer equipment and the ISP's border route to independently calculate the correct IPv4 address and port set for any given IPv6 address. This creates a completely stateless, deterministic system where no central binding table is required. The algorithm ensures that each customer receives a unique subset of ports on a shared IPv4 address, and both ends of the connection can compute these bindings on demand based purely on the IPv6 addresses involved. This eliminates synchronization issues, reduces operational complexity, and provides ultimate scalability. MAP addressing algorithm. The MAP addressing algorithm is the mathematical foundation that makes the entire system work. Understanding this algorithm is crucial to appreciating how MAP achieves its scalability and deterministic properties. The algorithm creates a reversible mapping between an IPv6 prefix assigned to a customer and the combination of an IPv4 address plus a port set ID. This mapping is based on a set of parameters called the MAP rule, which includes the end-user IPv6 prefix length, the IPv4 prefix being shared, the embedded address bits, and the port parameters, including offset and ratio. Let's walk through how the algorithm works with a concrete example. Suppose an ISP has an IPv4 prefix 203.0.113.0/24 that they want to share among customers. They've deployed IPv6 with a /40 allocation, and they want each customer to receive a /56 prefix. The MAP algorithm allows them to embed information about the customer's IPv4 address and port set directly into the IPv6 prefix. The algorithm extracts specific bits from the customer's IPv6 prefix and uses these bits to determine which IPv4 address the customer should use and what their PSID is. For instance, bits 41 through 48 of the IPv6 address might encode the last 8 bits of the IPv4 address, while bits 49 through 56 encode the PSID value. The elegance of this approach is that the mapping is bidirectional and deterministic. Given an IP version 6 address, You can calculate the IPv4 address and PSID given an IPv4 address and port number. You can calculate the corresponding IPv6 address. This BI directionality means that the customer's CPE, called a MAP customer edge or CE device, can determine its own IPv4 address and port set by examining its IPv6 prefix. Similarly, the ISP's border router, called a MAP border relay or BR, can determine which customer owns a particular IPv4 address and port combination by calculating the corresponding IPv6 address. No database lookups are required, just mathematical computation based on the MAP rule parameters. The algorithm handles port sets using the same bit manipulation techniques we saw in LW406, where specific bit positions in the port number are matched against the PSID to determine if a port is valid for a particular customer. MAPE encapsulation mode. MAPE, or MAP encapsulation, is the variant that uses IPv4 in IPv6 tunneling to transport packets across the ISP's network. From an architectural perspective, MAPE is very similar to LW406. The customer equipment performs port-restricted NAT using an algorithmically derived port set, then encapsulates the translated IPv4 packets in IPv6 for transmission across the IPv6-only network. The key difference between MAPE and LW406 is that MAPE uses the standardized map addressing algorithm for all calculations, whereas LW406 implementations might use various provisioning approaches. The MAPCE device in MAPE performs several functions. It receives its IPv6 prefix through standard IPv6 mechanisms like DHCPv6 prefix delegation or SLAAC. It also receives the MAP rule parameters, typically through DHCPv6 options, that describe how to perform the address and port calculations. Using these parameters and its assigned IPv6 prefix, the CE calculates its IPv4 address and PSID. It then configures itself to perform port-restricted NAT, translating private IPv4 addresses from the customer LAN to the derived public IPv4 address using only ports from its calculated port set. When forwarding packets to the Internet, the CE encapsulates them in IPv6 with a destination address that represents the MAP border relay. The MAP BR in MAPE operates in a stateless manner, similar to the LWAFTR in LW406. When it receives an encapsulated packet from a CE, it decapsulates it and validates that the source IPv4 address and port are consistent with what the MAP algorithm would calculate for the source IPv6 address. If validation passes, the packet is forwarded to the IPv4 Internet. For return traffic, the BR receives IPv4 packets destined for the shared address space. It examines the destination IPv4 address and port, uses the MAP algorithm to calculate which customer's IPv6 prefix corresponds to this IPv4 port combination, encapsulates the packet with that IPv6 address as the destination, and forwards it through the IPv6 network. The entire process is stateless because both the CE and BR can perform all necessary calculations independently based on the MAP rule and the addresses in the packets. MAPT translation mode. MAPT, or map translation, takes a fundamentally different approach to carrying IPv4 traffic across the IPv6 network. Instead of encapsulating IPv4 packets inside IPv6 packets, MAPT performs stateless protocol translation, converting IPv4 packet headers to IPv6 headers and vice versa. This approach has some significant advantages in terms of MTU handling and operational characteristics, but it also introduces additional complexity in the translation process. MAPT builds on the NAT64 stateless translation framework but adds the MAP addressing algorithm to create deterministic, stateless, bidirectional translation. The translation process in MAPT is intricate because it must maintain end-to-end transparency while converting between fundamentally different protocol versions. When a customer device sends an IP version 4 packet, the MAPCE translates it to IP version 6. The source IP version 4 address and port are mapped to an IP version 6 address using the MAP algorithm. The IP version 4 address bits and PSID bits are embedded in specific positions within the IP version 6 address according to the MAP rule. The destination IP version 4 address is also translated to IP version 6, either by looking up a destination mapping rule or by using an algorithmic translation for the default route. The resulting packet is pure IP version 6 and can be routed natively through the ISP's IP version 6 network without any encapsulation overhead. At the MAPBR, the translation process reverses. The BR receives an IPv6 packet and recognizes it as MAPT traffic based on the destination IPv6 prefix. It extracts the embedded IPv4 address and port information from the IPv6 source address using the MAP algorithm, reconstructs the original IPv4 source address and port, and translates the IPv6 destination address back to IPv4. The result is a standard IPv4 packet that can be forwarded to the IPv4 Internet. For return traffic, the process mirrors this. The BR receives an IPv4 packet, translates the source to IPv6 using appropriate rules, and embeds the destination IPv4 address and port into the IPv6 destination address using the MAP algorithm. The translated IPv6 packet is then routed to the customer. This stateless translation means the BR never needs to maintain per session state, enabling the same scalability benefits we saw with MAPE. MAP rule configuration. Configuring MAP requires careful planning and understanding of the MAP rule parameters that govern the entire system. The MAP rule is a structured set of information that defines how the mapping algorithm operates. Every MAPCE and MAPBR in the deployment must have consistent MAP rules to ensure the addressing algorithm produces compatible results. The rule defines several critical parameters that work together to create the mapping between IPv6 addresses and IPv4 address plus port combinations. The first key parameter is the rule IPv4 prefix, which specifies the pool of IPv4 addresses that will be shared using this MAP rule. For example, an ISP might specify 203.0.113.0/24. Indicating that all 256 addresses in this range are available for MAP assignment. The rule IPv6 prefix defines the IPv6 address space that will be mapped to this IPv4 pool. This might be something like 2001:db8:1000:40, representing a large block of IPv6 space that will be subdivided among customers. The end-user IPv6 prefix length specifies how much IPv6 space each customer receives, typically /56 or /64. Port parameters are equally critical. The embedded address bits, or EA bits, determine how many bits from the customer's IPv6 address are used to encode IPv4 address and port set information. This value is calculated based on the sharing ratio desired and the prefix lengths involved. The EA bits are subdivided into bits that encode the IPv4 address suffix and bits that encode the PSID. For example, if we are sharing a /24 IPv4 prefix among customers and we want 256 sharing ratios, we need 8 EA bits total. We might use 0 bits for IPv4 address selection if each customer gets a full address, or we might use 2 bits for IPv4 selection and 6 bits for PSID if we want a 4:1 sharing on the IPv4 side and a 64:1 sharing on the port side. The port parameters include the PSID offset and length, which determine the port set calculation algorithm. Finally, the rule includes the border relay IPv6 address for MAPE or the default mapping rule for MAPT translation. Packet processing in MAPE. Let's trace a complete packet flow through MAPE to understand the detailed processing at each step. Consider a customer who has been assigned the IPv6 prefix 2001:DB8:1234:5600:/56. The ISP's MAP rule specifies a rule IPv6 prefix of 2001:DB8:1234::/40. Rule IPv4 prefix of 203.0.113.0/24. EA bits of 16 with 8 bits for IPv4 address selection and 8 bits for PSID, and standard port parameters. A device on the customer LAN with private IP 192.168.1.100 wants to connect to a web server at 93.184.216.34. The customer device creates an IPv4 packet with source 192.168.1.100, destination 93.184.216.34, and random source port 54321. This packet reaches the MAP-CE. The CE first calculates its derived IPv4 address using the MAP algorithm. It extracts bits from its IPv6 prefix according to the EA bits specification. In this specific instance, bits 41 to 48 of the IPv6 address 2001:DB8:1234:5600 contain the value 0x56, which becomes the last octet of the IPv4 address, giving us 203.0.113.86. The CE then extracts its PSID from bits 49 to 56, which in this prefix contain 0x00, so PSID equals 0. Using this PSID, the CE calculates its valid port range. With PSID 0 and standard parameters, it might have ports 1024 to 1279. The CE performs NAT translation, replacing the source IP 192.168.1.100 with 203.0.113.86, and selecting an available port from its range, for example, 1100. It creates a NAT binding in its state table. The CE then encapsulates this translated IPv4 packet in an IPv6 header. The source IPv6 address is the CE address, derived from its prefix, perhaps 2001:DB8:1234:5600:1. The destination IPv6 address is the MAPBR address, such as 2001:DB8:FFFF:1. The packet travels across the IPv6 network to the BR. The BR decapsulates it and validates that the source IPv4 address 203.0.113.86 and port 1100 match what the algorithm would derive from the source IPv6 address 2001:DB8:1234:5600:1 with PSID 0. It confirms the validation and forwards the IPv4 packet to its destination. Return traffic arrives at the BR destined for 203.0.113.86:1100. The BR uses the MAP algorithm in reverse. It calculates that IPv4 address 203.0.113.86 with PSID 0 maps to IPv6 prefix 2001:DB8:1234:5600:/56. It then encapsulates the packet for that destination and forwards it to the CE. Packet processing in MAPT. MAPT packet processing is more complex due to the stateless translation requirements. Let's follow the same scenario as before, but with MAPT translation instead of encapsulation. The customer has the same IPv6 prefix 2001:DB8:1234:5600:/56, derives the same IPv4 address 203.0.113.86 and PSID 0, and performs the same NAT translation to convert the private source 192.168.1.100 to public 203.0.113.86:1100 with destination 93.184.216.34:80. Now, instead of encapsulation, the map CE performs IPv4 to IPv6 translation. It constructs an IPv6 source address by embedding the IPv4 source address and port, according to the map algorithm. The format might place the IPv4 address octets and PSID bits in specific positions within the IPv6 address structure. The result is an IPv6 source address like beginning with 20 ending with 4C, where the embedded bits encode 203.0.113.86, and port 1100. The destination IPv4 address 93.184.216.34 must also be translated to IPv6. The map CE consults its configured rules, which might specify that IPv4 destinations in the default range translate to IPv6 addresses in a specific prefix, or there might be a default mapping rule. The result might be an IPv6 destination like beginning with 20 ending with 22. The translated IPv6 packet travels through the IPv6 network as native IPv6 traffic. No encapsulation, no tunneling, just standard IPv6 routing. When it reaches the map BR, the BR recognizes the destination prefix as requiring map T translation back to IPv4. It translates the destination IPv6 address back to IPv4 address 93.184.216.34. It extracts the embedded IPv4 address and port from the source IPv6 address, reconstructing source 203.0.113.86:1100. The BR validates that these derived values are consistent with the map rule for the source IPv6 prefix. It then forwards the translated IPv4 packet to the destination. Return traffic arrives as IPv4 with source 93.184.216.34:80 and destination 203.0.113.86:1100. The BR translates the source to IPv6 using the appropriate mapping rule, embeds the destination IPv4 address and port into an IPv6 destination address using the map algorithm to calculate beginning with 20 ending with 4C, and forwards the translated IPv6 packet through the network to the customer. MAPE versus MAPT comparison. Choosing between MAPE and MAPT involves understanding the trade-offs between these two approaches. Both variants share the same addressing algorithm and provide the same basic functionality, that is, stateless IPv4 service over IPv6 only infrastructure with algorithmically determined port-restricted address sharing. However, they differ significantly in their operational characteristics, deployment considerations, and suitability for different environments. MAPE's encapsulation approach is conceptually simpler and more straightforward to implement. The IPv4 packet is preserved entirely within the IPv6 tunnel, which means that IPv4 characteristics, like fragmentation, options, and error messages, are handled naturally. The MAPCE and BR are essentially performing tunneling with validation, which is a well-understood operation. MAPE is generally easier to deploy because it does not require complex protocol translation. If your equipment can handle IPv4 and IPv6 tunneling and the MAP addressing algorithm, you can implement MAPE. The encapsulation also means that MAPE is more tolerant of IPv4 packets with unusual characteristics or edge cases that might be difficult to translate cleanly to IPv6. However, MAPE encapsulation comes with overhead. The IPv6 header adds 40 bytes to every packet, which reduces the effective MTU available for payload data. This overhead is particularly significant for small packets like voice over IP or gaming traffic where the payload might be comparable to the header size. The encapsulation also means that path MTU discovery becomes more complex. The IPv4 application sees a smaller effective MTU due to the encapsulation overhead. MAPT eliminates this overhead by translating rather than encapsulating. A 60-byte IPv4 packet becomes a 60-byte IPv6 packet rather than a 100-byte encapsulated packet. This makes MAPT more efficient from a bandwidth perspective and eliminates some of the MTU complexity. MAPT also has the advantage that the traffic appears as native IPv6 in the core network, which may be beneficial for certain monitoring, QoS, or security systems that need to inspect packet headers. The disadvantage is that MAPT translation is significantly more complex to implement correctly, particularly for handling edge cases like IPv4 fragments, IPv4 options, and ICMP messages that do not have direct IPv6 equivalents. Deployment and operations. Deploying MAP in a production environment requires careful planning of the addressing scheme and MAP rule parameters. The ISP must first decide on their IPv6 addressing structure. How much IPv6 space will be dedicated to MAP, what prefix length each customer will receive, and how the EA bits will be embedded in the IPv6 addresses. They must also determine their IPv4 sharing strategy, which IPv4 addresses or prefixes will be used for MAP, what sharing ratio is needed to accommodate all customers, and how to balance port availability against address conservation. The MAP rule design process involves mathematical calculations to ensure all parameters align correctly. The number of EA bits must equal the sum of the IPv4 address bits being shared plus the PSID length. For example, if an ISP has a /20 IPv4 prefix that they are as /32 individual addresses among customers with a 256:1 sharing ratio, they need 0 bits for IPv4 address selection, since each customer gets their own address, plus 8 bits for PSID, totaling 8 EA bits. These 8 bits must fit within the difference between the rule IPv6 prefix length and the end-user IPv6 prefix length. If the rule uses a /40 and customers get /56 prefixes, there are 16 bits available, which is more than sufficient for 8 EA bits. The port parameters must then be configured to allocate ports fairly. With 8-bit PSID and a standard offset of 6 bits, each customer gets approximately 252 ports distributed across the port space. Provisioning MAP involves configuring the MAP rules on both CE devices and BRs through DHCPv6 or other mechanisms. The MAP rule can be conveyed using DHCPv6 options specifically defined for MAP in RFC 7598. The CE receives its IPv6 prefix through normal IPv6 mechanisms, receives the MAP rule parameters, and calculates all necessary values automatically. The BR must be configured with the same MAP rules to ensure consistent operation. For operational monitoring, ISPs track metrics like CE device count, BR packet processing rates, port utilization per customer, and algorithm validation failures. One significant operational advantage of MAP is that troubleshooting is deterministic. Given any IPv4 address and port, you can immediately calculate which customer it belongs to without consulting any database. This makes tracking down issues, responding to abuse complaints, or investigating network problems much simpler than with dynamic carrier-grade NAT systems. MAP advantages in future. The MAP family represents the state-of-the-art in deterministic, stateless IPv6 transition mechanisms. The algorithmic approach to address and port mapping provides several compelling advantages over other transition technologies. The elimination of centralized state and binding tables means that MAP scales effectively to millions of customers with minimal infrastructure. The border relay doesn't need gigabytes of session state or binding tables. It only needs the MAP rule parameters and the mathematical ability to execute the algorithm. This makes MAP-BRS extremely fast and efficient, capable of line rate processing with simple hardware or software implementations. The deterministic nature of MAP provides operational benefits beyond just performance. Network operators can instantly determine which customer owns a particular IPv4 address and port combination by applying the reverse mapping algorithm. This is invaluable for troubleshooting, security investigations, and regulatory compliance. Unlike carrier-grade NAT systems where you need to query logs or state tables to determine customer associations, MAP provides instant, mathematical determination of ownership. The algorithmic approach also means that MAP deployments are highly resilient. If a BR fails, traffic can be instantly redirected to another BR without any state synchronization or loss of service because there is no state to synchronize. Looking toward the future, MAP continues to evolve with ongoing refinements and deployment experience. The technology is seeing significant adoption in Asia, particularly in Japan where multiple ISPs have deployed MAP-E at scale serving millions of subscribers. MAP-T has seen more limited adoption due to its implementation complexity, but it remains attractive for scenarios where the translation approach provides operational advantages. The MAP addressing algorithm is also being explored for other applications beyond basic IPv4 service continuity. Some proposals suggest using similar algorithmic approaches for IPv6 prefix delegation, multicast address assignment, or service function chaining. As IPv6 deployment continues globally, MAP provides a proven, scalable path for maintaining IPv4 service compatibility throughout the extended transition period. The mathematical elegance and operational efficiency of MAP make it particularly well suited for large carrier networks where scale, performance, and deterministic operation are paramount concerns. Thank you for your attendance. Please consider subscribing to the channel.